as we've seen, Faraday's law, or Faraday's law of electromagnetic induction, says you get a voltage created, which I'm calling E, that EMF, anytime you change the magnetic flux with time. We've defined magnetic flux earlier in the PowerPoint. And if you have a magnetic flux change through a coil, which has N number of loops, you get, the bigger N is, the more volts you get induced. Lenz's law, we've said, determines the direction of the induced current that is created by this induced voltage if you have a conductor that the current can flow in. And Lenz's law says the induced current will create a magnetic field, and that magnetic field will oppose the change in the magnetic flux. It doesn't oppose the flux, it opposes the change in the flux. So if the flux gets bigger, the induced field will try to keep it from getting bigger. It'll fight it. If the flux is decreasing, the induced field will try to build it back up. Okay? And remember, flux relates to the number of field lines going through a loop. So we'll see that'll help us analyze a simple situation. So here I've got a long straight current carrying wire carrying current I, and next to it I just have a loop of wire. Okay, there's no battery or anything, it's just a loop of wire sitting next to that current carrying wire. If the current I is constant, what will happen? If this current in the wire is constant, then there'll be a constant magnetic field surrounding it. Our very first right-hand rule says thumb in the direction of current, circular field, curl your fingers around. Your fingers will be poking in over here where this loop is. So there's a magnetic field due to the wire that points in. I'll call that B wire, and I'm showing it pointing in with that X. But because this current is constant, that magnetic field is constant. So you have a constant number of field lines passing through this loop. That means there's no change in the magnetic flux. You have a constant magnetic flux. If there's no change in flux, there's no voltage induced and no current flows in the loop. So we could say no induced current. So that's a simple case. But what if I is increasing? What if that current in that long straight wire is getting bigger? What happens now? So if this current's getting bigger, that means its magnetic field's getting bigger with time. So that means you're going to have more and more field lines passing through this loop as time goes on. That's an increase in magnetic flux. So if you have a change, you're going to get volts, and if you have a conducting loop like we do, you're going to get current to flow. So current's going to flow in this loop. If you're a guesser, you could just guess which way it's going to flow. It's got to be clockwise or counterclockwise. Those are the only two options. But let's use Lenz's law to get the exact direction. So we have a field poking in that's getting bigger due to the increasing current. Lenz's law says the induced current will create a field that opposes the change in the flux. So we have a field going in, getting bigger, increasing flux with the field going in. How do we keep the flux from getting bigger? Create a field out. That'll cancel some of the field lines going in. So we want an induced field out. So I'll draw a circle with a dot and say the induced field, the field created by the induced current, has to be coming out to fight that increasing field going in. Okay, so we had a right-hand rule for loops that says if you point your thumb in the direction of the field in the middle, your fingers will curl around in the direction of the current. So that means the current, the induced current, must be traveling counterclockwise to make my induced field out. So the induced current flows counterclockwise. Counterclockwise. Okay? CCW. Okay, so by simply changing this current, we're going to create current in this other loop that's going to flow counterclockwise. Okay, what would happen if I is decreasing? So if the current in this wire is decreasing, that means this field is getting weaker now with time. It's poking in still, the field of the wire, but it's getting smaller because the current's getting smaller. So that's a decrease in flux with the field going in, fewer and fewer field lines poking in. Lenz's law says you want to oppose the change in the flux. So weakening field going in, a decrease in flux with the field going in, how do you build it back up? How do you make the flux stop getting smaller? Well, you increase the flux back to its normal state by having a field poking in. So we need an induced field that will go in now to build up the decreasing field due to the wire which pokes in. Okay, that means the induced current will flow in the opposite direction. Again, because if you curl your fingers in around the loop and the way the current flows, your thumb points in the direction of the field's going in, so the current must go clockwise now. So I induced is clockwise when the current in this wire is decreasing. Incidentally, this is a way to create a wire tap. Back in the old days when people had phones with wires, if this was a phone line, you could simply put a coil next to, or a loop next to that phone line, and as the person talked or data was going over that phone line, its magnetic field would fluctuate with time, so the field due to the phone line would change. That would induce current in the wire in direct proportion and at the same frequency of the change. So you could, for instance, listen in. You could put a pair of headphones, for instance, on, and you'd be able to listen in because there would be an induced current flowing one way or the other as this current changes. You get an induced current. You might have to amplify it to make it a little bit louder. And a way to make it even better would be to wrap a coil from your loop around that phone line. Because again, the more loops you have, the bigger N is, the bigger the volts induced, the bigger the current flows. So you'll get even a stronger current flowing around your loop, and you'd be able to listen in even better. This has been done, was done a lot in the early days before cell phones. For instance, the US Navy in the early 1950s got in a submarine and went to the bottom of the Pacific Ocean where they found a cable that the Soviet Union had connected from the western part of Soviet, or eastern part of Soviet Union over to their embassy in San Francisco. They didn't want to use radio communications to communicate with their embassy because people could listen in on it. So they buried a cable in the ocean, on the ocean floor, and could talk over a phone line. Well, the Navy got down 10,000 feet down in the ocean and wrapped a coil around that line that the Soviets had laid, and we listened in on all their conversations for about 10 years before they figured it out. They were probably doing the same to us.